Let us next see exercise 10. In this one we have a prime p of the form 4k plus 3. So p is an odd prime specifically of this form. So it is not of that other form 4k plus 1. If so, then prove that either p minus 1 over 2 factorial is congruent to 1 modulo p or congruent to minus 1 modulo p. So that is part A. And in part B we have to use part A to prove that the product of all the even integers less than p is congruent modulo p to either plus 1 or minus 1, just like this one. And p of course is of that form. So let us first see the solution to part A. So here you can recall how we proved that result, our last result, theorem 5.5. Since P is of the form 4k plus 3 proceeding as in the second part of that theorem, part of theorem 5.5, we get this congruence p minus 1 over 2 factorial square is congruent to 1 modulo p. What does this mean? It means that p divides this square minus 1. To that you can apply the a square minus b squared formula. So p would then divide this factorial plus 1 times that factorial minus 1. And because p is prime, it divides either of them. Okay, either it divides one or the other. Maybe both, who knows. Well, it cannot divide both because it's odd. In that case, it has to divide 2. But anyway, it divides one of them. So that's how we get our part A. So we can write like this: since P is prime, this implies, let me write at once, okay, P minus 1 over 2 factorial is congruent to either 1 or minus 1 modulo P. So that is our part A. B. In part B, we have to consider all the positive even integers less than P, because P itself is odd, so P minus 1 is also even. So our product will get till P minus 1. Let's consider the product straight away. 2 times 4 times 6 and so on, P minus 1. So what we can do is we can take all the 2's together and form a power of 2. 2 to the power. The question is how many 2's there are in this product. Well, the first 2 is 2 times 1, the second one is 2 times 2, the third one is 2 times 3, and this one is 2 times P minus 1 divided by 2. So that many 2's we have, that is 2 to the power P minus 1 over 2. And then after taking all the 2's together, you are left with 1, 2, 3 and so on up to this P minus 1 over 2. So its factorial is what we have here. Alright. Now, well, I should of course write the modulus. Actually, you can simply, without writing a congruence, you can simply write equal to this. But because we are anyway going to consider congruence, so I wrote it in this form. Alright. Now, in place of this factorial, you can actually write plus or minus 1. However, what do you do about this power of 2? So here Fermat's theorem is going to help us. Now, by Fermat's theorem, two to the power p minus 1 is congruent to 1 modulo p. Again, keep in mind that we are able to write like this because p is an odd prime, so p does not divide 2. Or 2 to the power p minus 1 divided by 2 square this. Note that you are able to write like this and still this exponent is an integer because p is odd. And just like you concluded this congruence from this one also we are going to get next this. Hence, 2 to the power p minus 1 divided by 2 is congruent to plus or minus 1 modulo p. So now you know that just like this one is congruent to plus or minus 1 modulo p, so is this one. So we can now use that fact. Hence, going back to that, 2 times 4 times 6 and so on up to p minus 1 is this times p minus 1 over 2 factorial. We can keep writing modulo p if you want. So this is plus or minus 1. This is also plus or minus 1. Note that we don't really know which one is 1 when and which one is minus 1 when, but it does not matter because whatever the quantities are, we are eventually going to get either plus 1 or minus 1. So that is what we wanted to show. So this is the solution. Okay, so the next one is 12. Here we again have a prime of that form 4k plus 3. And it's also given that a and b are integers such that a square plus b square is congruent to 0 mod p. We then have to show that a and b are individually congruent to 0 mod p, both of them. So the solution will be by contradiction. Suppose that a is not congruent to 0 modulo p. So essentially that just means that p does not divide a. That means they are relatively prime. That is another way of looking at it. Then there exists an integer c such that AC is congruent to 1 modulo p. The existence of this C comes from the theory of linear congruences. Because P does not divide A, this means that the GCD of A and P is 1. So the linear congruence AX congruent to 1 modulo P will have a unique solution. So unique solution modulo P, of course. So this C is one such integer. Okay, so it exists. Now let us consider this 1 plus AC square, or well, not exactly 1 plus AC square, 1 plus BC square, yes, since, and we are now going to use this congruence. A square plus B square is congruent to 0 modulo P. We have 1 plus BC square is going to be congruent to, if our modulus is P, AC square plus BC square, because AC is congruent to 1 not P, and this is A square plus B square times C square, which is congruent to 0 modulo P. Okay. However, what do we then have? Then this thing is contradicting theorem 5.5, that means that result, existence of solution to that congruence. Okay, x square congruent to -1 modulo P. You know from that result, theorem 5.5, that congruence has a solution if and only if P is of the form 4k plus 1, which means that for our prime P, which is of the form 4k plus 3, there should be no solution to x square congruent to -1 mod P. Or in other words, there should be no integer whose square to that if you add 1 should you get congruent to 0 mod P, but that is precisely what we are getting here. So that means something has gone wrong. Theorem 5.5 has been contradicted. So what went wrong is actually our supposition, which cannot be true. But this contradicts theorem 5.5 since P is of the form 4k plus 3, or P is congruent to 3 modulo 4. Thus, we cannot have that. That is, we must have mod P. Similarly, B is also congruent to 0 mod P. So that's the solution. Is 14th. Prove that the odd prime divisors of this integer of the form n square plus 1 must all be of the form 4k plus 1. Let's see how. This again has to do with theorem 5.5. Suppose this is not true. That means this number has at least one prime divisor, odd prime divisor, which is of the form 4k plus 3. Suppose n square plus 1 has a prime divisor P of the form 4k plus 3. Now P is dividing n square plus 1 means what? Then n square plus 1 is congruent to 0 modulo P. But then this directly contradicts theorem 5.5 again, just like that one. But this contradicts so our supposition is wrong. That means no odd prime of n square plus 1 can be of this form. However, then it has only that other available form, namely 4k plus 1. So there you have the solution. Okay, so next we have 16. Here a prime is given, not of any special form, just a prime is given, and some integer k is given which is non-negative and less than p, or less than or equal to p minus 1. Then we have to prove that k factorial times p minus k minus 1 factorial is congruent to minus 1 to the power k plus 1 modulo p. Now, among the many possible values of k, let us first see what this congruence becomes when k is equal to 0, the simplest possible value. 0 factorial is 1, and here we have p minus 1. So, the left hand side becomes p minus 1 factorial. What happens to this? Because k is 0, this becomes minus 1. So, p minus 1 factorial is congruent to minus 1 modulo p, which is just Wilson's theorem. So, accordingly, let us start the solution with this observation. For k equal to 0, the claim is just Wilson's theorem. So, we can now assume that k is positive because this case has been settled, it is already settled. And now we will have to take the help of an exercise that we saw in the previous exercise set, that is 5.3. Exercise 12 from exercise 12 of section 5.3. What was that exercise? It tells us that for this type of k, p minus 1 choose k, that binomial coefficient, is congruent to minus 1 to the power k modulo p, that exercise. So, let me write like this: p minus 1 factorial divided by k factorial times this. So, this quantity is, of course, it is just this binomial coefficient, which by this exercise is congruent to minus 1 to the power k modulo p. So, if you now multiply on both sides by this denominator, which you can do because it is the congruence, you can multiply on both sides by any integer, you will then get p minus 1 factorial is congruent to this k factorial times p minus k minus 1 factorial times minus 1 to the power k mod p, or now we can multiply on both sides by minus 1 to the power k, that also we can do. And if we do that, this will come to this side, and on this side it will be minus 1 to the power 2k, which of course will become 1. That is, we will then have this. This is congruent to k factorial times p minus k minus 1 factorial modulo p. We use Wilson's theorem once, and we have to just interchange the sides of this congruence. So, by Wilson's theorem, so we write this side first, k factorial times factorial is congruent to minus 1. Let's first write the entire thing. Okay, so this will then further be congruent to times minus 1. So here we used Wilson's theorem because p minus 1 factorial is congruent to minus 1. Modulo, now if we continue, then it becomes this. So that's what we wanted to show. So that is the solution. Here we have two primes, p and p plus 2. P plus 2 is also prime, so they formed a pair of twin primes. If so, then we have to prove that 4 times p minus 1 factorial plus 1 plus p is congruent to 0 modulo this integer, which is the product of these two. Okay, so let's see how we can establish this. By Wilson's theorem, let's first focus on the modulus p. Yeah, we need this modulus, but we will consider these two primes separately and then we will combine them. So for the prime p, we straight away get something from Wilson's theorem. So this will be, so p minus 1 is congruent to minus 1. That means this is congruent to p, which is congruent to 0 mod p. So whatever congruence we want, we actually are having that for the modulus p. Now next comes the modulus p plus 2. Now for the modulus p plus 2, we won't write simply this, but with this we write something else also. We write p times p plus 1 and then we write that thing plus 1 plus p. Let's do the multiplication and let's see how it helps. So you can see that with p minus 1 factorial, 4 is also there, but with this factorial we will multiply p and p plus 1. So that will give us p plus 1 factorial with 4. P plus 1 factorial plus 4 times p plus 1 plus p square times p plus 1. Alright. Now let us bring in the modulus p plus 2. Things have changed a little bit and now we can see a pattern here, because p plus 1 is p plus 2 minus 1 factorial. What about this? We can write p plus 2 minus 2 times p plus 2 minus 1. Similarly here, p plus 2 minus 2 square times p plus 2 minus 1. Now considering that our modulus is p plus 2, what shall we get? You see, do not just simply remove p plus 2 and write minus 1 factorial. Don't do that, okay? Instead, you can apply Wilson's theorem here. Because our p plus 2 itself is a prime and that is the modulus, so this factorial is congruent to minus 1. So 4 times minus 1. From these simple things, however, which do not have factorial, we get 4 times minus 2 times minus 1. And from this last one we get minus 2 square times minus 1. Has been made simple. So what are we getting from here? Minus 4. What shall we get from this second term? Plus 8. And from this one, this is 4 but there is a minus. So you can see that this is also congruent to 0, but now the modulus is p plus 2. And finally you can combine the moduli because they are relatively prime to each other. Since this is equal to 1, four times this plus p is congruent to 0 mod p times p plus 2. And that's it. That is our solution. And that concludes this section and this chapter. In fact, after this we have numbered theoretic functions in the next chapter that we will start next. And tomorrow also we have our usual upload. So see you tomorrow with a new video. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.